Welcome back to Learning with me, Ms. Killen, here at MPB. We've done it. This is our last lesson in Unit 11. This is our last lesson in Algebra 1. So we're almost at the end. Let's get through Lesson 5, and then we will have learned everything there is in our Algebra 1 curriculum. Here we go. So Unit 11, Lesson 5, Analyzing Patterns, Correlation, and Causation. I can calculate, interpret in data, and distinguish between correlation and causation. We are looking at SID 6C, 8, and 9. So let's jump right in. We have new vocabulary, correlation, which shows the relationship between two variables, our correlation coefficient that we're going to look at in just a minute, and our causation, what causes something to happen. So here's a passage. Let's examine the trend of Christmas gifts given in Mississippi from 1974 to 1991 using the scatter plot. The data below represents the average number of Christmas gifts given per household in Mississippi for each year from 1974. So let's see these scatter plots. So we have our years and our gifts. So we want to describe the relationship between the data from 1974 to 1988. Do we see an increase or decrease? So what you can do is go ahead and plug this into Desmos. Look to see what information it gives you. Look to see the trend or line of best fit for this data. We also want to see, are the data points close to the line of best fit, or are they loosely scattered around the line? So we also want to see if they are close to that line. So I went ahead and I graphed these in my Desmos, and I see that it is an increase for our gifts from 74 to 91, specifically an increase between 74 and 88. Next thing I want us to see is we could have a line of best fit that looks something similar to this. Now, obviously, Ms. Killen still can't draw a straight line, but that would be something similar to our line of best fit. When you plug these into Desmos, you are going to get your information. So I have y equals 0.847x minus. So we would say that this is close to our line of best fit. We're wanting to remember how we plug that graph in and how we pull the information for our line of best fit M and B. Information we need in our notes. We need to know what our linear regression is. The form is our y equals mx plus b. We use it when data forms a straight line pattern. Remember, it's not going to be an exact path of a linear line, but it's going to have that straight line pattern. An example is predicting costs based on hours worked. The next one we're looking at is our quadratic regression. The form is y equals ax squared plus bx plus c. We use this when the data forms a parabola-like shaped curve. The example is modeling the path of an object. Maybe we're kicking a ball or we're hitting a golf ball off a tee. The next one is our exponential regression. The form obviously is y equals ab to the x. We use this when the data shows a rapid growth, which is an increase, or a rapid decay, which is a decrease. And a lot of examples are going to be about population growth or radioactive decay when we see that slow to start and then the growth or the decay. Our last one is our cubic regression, and we don't really look at this one until we get into some of that upper math, but I did want to go ahead and give you this cubic regression. So this cubic regression form is ax to the third plus bx squared plus cx plus d. We use this when data curves more than once. So we may have something that looks along the terms of this or this. And our example is complex real-world patterns, like a roller coaster path. So we want to make sure as we get more into our math that we're remembering these different four regressions. These regression models help us learn how to fit curves of data, interpret trends, and make predictions based on their mathematical relationships. So my correlation coefficient, which is our R, measures the strength and the direction of the linear association between two quantitative variables. When dealing with patterns and the strength of correlation, you have a positive or a negative 1. The closer the coefficient is to a negative 1 or a positive 1, the stronger that correlation or that relationship is. The closer it is to 0, then you have a weaker correlation where the scatter plot is going to be everywhere. The closer to the trend line the points are, the larger the absolute value of that R will be. So let's look at this. Use the following correlation coefficients and determine if they are weak or if they are strong. I'm going to give you about 15 seconds. Just look at the numbers. See if you can figure out, are they weak or are they strong, knowing that you have from negative 1 to a positive 1. So go ahead and look at these and come back to me. All right, so our first one is R equals negative 0.001. Now that is almost to 0. So this is going to be extremely weak correlation. Our next one is negative, but that's okay. We have negative 0.541. So that's going to be about right here. Where it's not super strong, it's not weak. So we're going to say that it would be a moderate strong. The next one is 0.991. Now, that is almost knocking on positive 1's door, so we're going to say that this is a strong correlation. We have 0.791. Now, it is not as close to 1 as our previous, but it is going to be moderately strong, meaning in the middle of strength. We're looking at 0.1009. Now that's going to be about down here, almost to 0, but not quite. So we're going to say that this one has a weak correlation. And then we have 0.909. So we are really almost to 1, so this is going to be very strong correlation. So this is how we are looking at those correlation coefficients, depending on if we have a strong correlation, meaning a close association, or if we really don't have any association whatsoever when it comes to our two variables. So here is a very good representation of this correlation coefficient. We have a strong negative correlation. The closer you get to the negative 1, you have a strong positive correlation. The closer you get to a positive 1. Then you have this medium, or that moderate that we talked about, and then you have the very weak correlation. The scale ranges from negative 1, which is a strong negative correlation shown in red, to 0, which is no correlation whatsoever, to a positive 1, which is a positive strong correlation, which is shown in your blue and your blue-green. The slider visually indicates the strength and the direction of the correlation. So you have your strong correlation, you have your weak correlation, you have your strong positive correlation, and you have your positive, your strong negative correlation when you're looking at these coefficients. To see the strength of the coefficients from your calculator. Now, this is how you pull up that correlation coefficient's strength. This is the exact how to do. You go into your second key, and then how you go into your catalog, and how you do everything that you need to do to that calculator to make sure that it shows your coefficient. So when we do all that, we are looking right here. This stat diagnosis, and you want to turn it on. That's what you're wanting to do. If you will put the stat diagnosis on, when you pull that linear regression, it's going to show what that R is, how strong it is, or how weak it is. So that's another way that we are using our technology tools to help us answer these different questions with this correlation. All right, correlation does not mean causation. Okay, when something causes something, it's the causation. Okay, if I put my shoes on, then I won't hurt my feet when I step on the rocks, okay? So if I don't put my shoes on, I will hurt my feet. So there's a causation there. So a causation is a relationship between two variables when and where one variable directly affects or influences the other. This means that a change in one variable will cause a corresponding change in the other, not just a coincidence. Correlation versus causation. Correlation simply means two variables are related, but it does not mean one causes the other. So let's look at this. Correlation versus causation. Example. Ice cream sales and sunburns might be correlated, both increase in the summer. Do you think an ice cream sale is going to cause sunburns? No, it doesn't. They may have a correlation, but eating ice cream does not cause the sunburn. It just doesn't. The sun does that. All right, causation simply implies a direct effect. A change in one variable directly leads to a predictable change in another. So here's an example. The amount of time a student spends studying will likely cause a change in their test score. As we saw earlier, the more time that they had in their sleep, the better their scores were. Let's do some practice one more time. There's a strong positive association between the amount of fire damage, Y, and the number of firefighters on the scene, X. We see this happening in California. Does having more fighters on the scene cause greater fire damage? Why or why not? Well, it doesn't cause any more fire damage. The fire's causing the damage. Having the firefighters there is not affecting that fire damage whatsoever. So it's not a causation. It may help not have as much, but it's not causing the damage. All right, time for you to master it. The following statements either indicate a relationship of correlation or of correlation and causation. So you and your table partner, one more time, take time, pause the video, answer these questions, come back to me, and let's see what we got. All right, so we have football players who read more books, write better school papers. So is that just a coincidence, or them reading more is helping them writing better papers? Well, you don't know what type of books they're reading. They may be reading anime. They may be reading the dictionary. You don't know. So that is just a correlation. All right, what about an increase in eating pizza increases the number of calories consumed by a person? Well, obviously, pizza has a good many calories, so that is a correlation and a causation. Teams with many members spend more money on food. Well, if you're having a pizza party for a small team, you're not going to spend as much money as if you spend for that same amount of food for a larger group. So the larger the people, the more money you're having to spend on food. So obviously, you've got some type of correlation, and that correlation is causing that different amount that you're spending for the food. So it does have a correlation and a causation. One last thing to remember, what our correlation is and what it means. We are having a relationship. It doesn't mean that we're going to change something because of that relationship, but we do have a relationship. And what is our causation and how does it affect? When something happens, it is going to initially affect something else. I have had such an amazing time learning with you here at MPB. I am so excited to be able to say that we have worked through all of our lessons. We have worked through all of our standards. I know that you are going to go and do a great, great thing. As always, thank you for learning with me, Ms. Killen, and have an awesome day.